In chemistry, esters are classes of chemical compounds. Esters are usually derived from an inorganic acid or organic acid in which at least one OH group is replaced by an O-alkyl group. Commonly, esters are derived from carboxylic acids and alcohol. Esters comprise most naturally occurring fats and oils, which are fatty acid esters of glycerol. Esters with low molecular weight are commonly used as fragrances and found in essential oils and pheromones. Phosphoesters form the backbone of DNA molecules. Nitrate esters, such as nitroglycerin, are known for their explosive properties, while polyesters are important plastics, with monomers linked by ester moieties. Nomenclature, etymology. The word ester was coined in 1848 by German chemist Leopold Gmelin, probably as a contraction of the German Essiger currency there, acetic ether. IUPAC nomenclature of esters. Ester names are derived from the parent alcohol and the parent acid, where the latter may be inorganic or an inorganic acid. Esters derived from the simplest carboxylic acids are commonly named according to the more traditional, so-called trivial names, for example as formate, acetate, propionate, and butyrate, as opposed to the IUPAC nomenclature methanoate, ethanoate, propanoate and butanoate. Esters derived from more complex carboxylic acids are, on the other hand, more frequently named using the systematic IUPAC name, based on the name for the acid followed by the suffix -ote. For example, the ester hexyl octanoate, also known under the trivial name hexyl caprylate, has the formula CH3, CH2, 6CO2, CH2, 5CH3. The chemical formulas of organic esters are typically written in the format of RCO2R, where R and R are the hydrocarbon parts of the carboxylic acid and alcohol, respectively. For example, butyl acetate, derived from butanol and acetic acid, would be written CH3 Colorado, 2C4, H9. Alternative presentations are common, including BUOAC and CH3COOC4H9. Cyclic esters are called lactones, regardless of whether they are derived from an organic or an inorganic acid. One example of a lactone is gamma-valorolactone. Autoesters, an uncommon class of organic esters, are the autoesters, which have the formula RC-OA3. Triethylorthoformate 3, is derived, in terms of its name, from orthoformic acid 3, and ethanol. Inorganic esters. Ester is a general term for the product derived from the condensation of an acid and an alcohol. Thus, the nomenclature extends to inorganic oxoacids, for example phosphoric acid, sulfuric acid, nitric acid and boric acid. For example, triphenyl phosphate is the ester derived from phosphoric acid and phenol. Organic carbonates, such as ethylene carbonate, are derived from carbonic acid and ethylene glycol. Structure and bonding. Esters contain a carbonyl center, which gives rise to 120 degrees Celsius CO and OCO angles. Unlike amides, esters are structurally flexible functional groups because rotation about the COC bonds has a low barrier. Their flexibility and low polarity is manifested in their physical properties. They tend to be less rigid and more volatile than the corresponding amides. The pKa of the alpha hydrogens on esters is around 25. Physical properties and characterization. Esters are more polar than ethers but less polar than alcohols. They participate in hydrogen bonds as hydrogen bond acceptors, but cannot act as hydrogen bond donors, unlike their parent alcohols. This ability to participate in hydrogen bonding confers some water solubility. Because of their lack of hydrogen bond donating ability, esters do not self-associate. Consequently, esters are more volatile than carboxylic acids of similar molecular weight. Characterization and analysis. Esters are usually identified by gas chromatography, taking advantage of their volatility. IR spectra for esters feature an intense sharp band in the range 1730–1750 ACMA1 assigned to I1/2 carat equals O. This peak changes depending on the functional groups attached to the carbonyl. For example, a benzene ring or double bond in conjugation with the carbonyl will bring the wave number down about 30 ACMA1. Applications and occurrence. Esters are widespread in nature and are widely used in industry. In nature, fats are, in general, tree esters derived from glycerol and fatty acids. Esters are responsible for the aroma of many fruits, including apples, durians, pears, bananas, pineapples, and strawberries. Several billion kilograms of polyesters are produced industrially annually, important products being polyethylene terephthalate, acrylate esters, and cellulose acetate. Preparation: esterification is the general name for a chemical reaction in which two reactants form an ester as the reaction product. Esters are common in organic chemistry and biological materials, and often have a characteristic pleasant, fruity odor. This leads to their extensive use in the fragrance and flavor industry. Ester bonds are also found in many polymers. Esterification of carboxylic acids: the classic synthesis is the Fischer esterification, which involves treating a carboxylic acid with an alcohol in the presence of a dehydrating agent, RCO2H plus Rho RCO2A plus H2O. The equilibrium constant for such reactions is about 5 for typical esters, for example, ethyl acetate. The reaction is slow in the absence of a catalyst. Sulfuric acid is a typical catalyst for this reaction. Many other acids are also used, such as polymeric sulfonic acids. Since esterification is highly reversible, the yield of the ester can be improved using Le Chatelier's principle, using the alcohol in large excess. Using a dehydrating agent, sulfuric acid not only catalyzes the reaction but sequesters water. Other drying agents such as molecular sieves are also effective. Removal of water by physical means such as distillation as a low-boiling azeotropes with toluene, in conjunction with a Dean-Stark apparatus. Reagents are known that drive the dehydration of mixtures of alcohols and carboxylic acids. One example is the Stegleich esterification, which is a method of forming esters under mild conditions. The method is popular in peptide synthesis, where the substrates are sensitive to harsh conditions like high heat. DCC is used to activate the carboxylic acid to further reaction. DMAP is used as an acyl transfer catalyst. Another method for the dehydration of mixtures of alcohols and carboxylic acids is the Mitsunobu reaction, RCO2H plus Rho plus P, C6H5, 3 plus A2N2 RCO2A plus OP, C6H5, 3 plus A2N2H2. Carboxylic acids can be esterified using diazomethane, RCO2H plus CH2N2 RCO2CH3 plus N2. Using this diazomethane, mixtures of carboxylic acids can be converted to their methyl esters in near quantitative yields, for example, for analysis by gas chromatography. The method is useful in specialized organic synthetic operations but is considered too expensive for large-scale applications. Alkoholysis of acyl chlorides and acid anhydrides. Alcohols react with acyl chlorides and acid anhydrides to give esters, RCOCl plus Rho RCO2A plus HCl, RCO2O plus Rho RCO2A plus RCO2H. The reactions are irreversible, simplifying workup. Since acyl chlorides and acid anhydrides also react with water, anhydrous conditions are preferred. The analogous acylations of amines to give amides are less sensitive because amines are stronger nucleophiles and react more rapidly than does water. This method is employed only for laboratory-scale procedures, as it is expensive. Alkylation of carboxylate salts. Although not widely employed for esterifications, salts of carboxylate anions can be alkylating agent with alkyl halides to give esters. In the case that an alkyl chloride is used, an iodide salt can catalyze the reaction. The carboxylate salt is often generated in situ. In difficult cases, the silver carboxylate may be used, since the silver ion coordinates to the halide, aiding its departure and improving the reaction rate. This reaction can suffer from anion availability problems and, therefore, can benefit from the addition of phase transfer catalysts or highly polar aprotic solvents such as DMF. Transesterification. Transesterification, which involves changing one ester into another one, is widely practiced. RCO2A plus CH3OH RCO2CH3 plus Rho. Like the hydrolysation, transesterification is catalyzed by acids and bases. The reaction is widely used for degrading triglycerides, for example in the production of fatty acid esters and alcohols. Polyethylene terephthalate is produced by the transesterification of dimethyl terephthalate and ethylene glycol. C6H4, CO2CH3, 2 plus 2C2H4, OH, 2 or 1/N, C6H4, CO2, 2, C2H4, N plus 2CH3OH. Carbonylation, alkanes undergo hydroesterification in the presence of metal carbonyl catalysts. Esters of propionic acid are produced commercially by this method, C2H4 plus Rho plus company C2H5CO2R. The carbonylation of methanol yields methyl formate, which is the main commercial source of formic acid. The reaction is catalyzed by sodium ethoxide, CH3OH plus company CH3O2CH, addition of carboxylic acids to alkanes, in the presence of palladium-based catalysts, ethylene, acetic acid, and oxygen react to give vinyl acetate, C2H4 plus CH3CO2H plus 1/2O2 C2H3O2CCH3 plus H2O. Direct routes to this same ester are not possible because vinyl alcohol is unstable. Other methods: Dvorsky rearrangement of I plus or minus haloctanones in presence of base, Baeyer-Villiger oxidation of ketones with peroxides, Pinner reaction of nitriles with an alcohol, nucleophilic abstraction of a metal-acyl complex, hydrolysis of autoesters in aqueous acid, cellulolysis via esterification, reactions. Esters react with nucleophiles at the carbonyl carbon. The carbonyl is weakly electrophilic but is attacked by strong nucleophiles. The CH bonds adjacent to the carbonyl are weakly acidic but undergo deprotonation with strong bases. This process is the one that usually initiates condensation reactions. The carbonyl oxygen is weakly basic but forms adducts. Addition of nucleophiles at carbonyl. Esterification is a reversible reaction. Esters undergo hydrolysis under acid and basic conditions. Under acidic conditions, the reaction is the reverse reaction of the Fischer esterification. Under basic conditions, hydroxide acts as a nucleophile, while an alkoxide is the leaving group. This reaction, saponification, is the basis of soap making. The alkoxide group may also be displaced by stronger nucleophiles such as ammonia or primary or secondary amines to give amides. RCO2 plus NH2R RCONHR plus Rho. This reaction is not usually reversible. Hydrazines and hydroxylamine can be used in place of amines. Esters can be converted to isocyanates through intermediate hydroxamic acids in the Lawson rearrangement. Sources of carbon nucleophiles, for example, Grignard reagents and organolithium compounds, add readily to the carbonyl. Reduction: compared to ketones and aldehydes, esters are relatively resistant to reduction. The introduction of catalytic hydrogenation in the early part of the 20th century was a breakthrough. Esters of fatty acids are hydrogenated to fatty alcohols. RCO2 plus 2 hours to RCH2OH plus Rho. A typical catalyst is copper chromite. Prior to the development of catalytic hydrogenation, esters were reduced on a large scale using the Bouvard-Blanc reduction. This method, which is largely obsolete, uses sodium in the presence of proton sources. Especially for fine chemical syntheses, lithium aluminium hydride is used to reduce esters to two primary alcohols. The related reagent sodium borohydride is slow in this reaction. DIBAH reduces esters to aldehydes. Claisen condensation and related reactions. As for aldehydes, the hydrogen atoms on the carbon adjacent the carboxyl group in esters are sufficiently acidic to undergo deprotonation, which in turn leads to a variety of useful reactions. Deprotonation requires relatively strong bases, such as alkoxides. Deprotonation gives a nucleophilic enolate, which can further react, for example, the Claisen condensation and its intramolecular equivalent, the Dierckmann condensation. This conversion is exploited in the malonic ester synthesis, wherein the diester of malonic acid reacts with an electrophile, and is subsequently decarboxylated. Another variation is the Fratira-Urosebch alkylation. Other reactions, Phenol esters react to hydroxyalketones in the Fries rearrangement. Specific esters are functionalized with an I+ or minus hydroxyl group in the Chan rearrangement. Esters with I² hydrogen atoms can be converted to alkanes in ester pyrolysis. Protecting groups. As a class, esters serve as protecting groups for carboxylic acids. Protecting a carboxylic acid is useful in peptide synthesis, to prevent self-reactions of the bifunctional amino acids. Methyl and ethyl esters are commonly available for many amino acids. The T-butyl ester tends to be more expensive. However, T-butyl esters are particularly useful because, under strongly acidic conditions, the T-butyl esters undergo elimination to give the carboxylic acid and isobutylene, simplifying workup. List of esterodorants. Many esters have distinctive fruit-like odors, and many occur naturally in the essential oils of plants. This has also led to their commonplace use in artificial flavorings and fragrances when those odors aim to be mimicked. See also, cyanate ester, oligoester, polyol ester, transesterification, transamidification. References. External links, An Introduction to Esters, Molecule of the Month, Ethyl acetate and Other Esters.